we would need to show that f equal to kx condition is satisfied. So let's say at an instant the particle is here where this is x. The tunnel is like this. Construct a surface like this This construction is only for solving this problem. Now you know the rule from gravitation topic. If some particle manages to reach here, how will Earth attract it? Only the inner part will attract the particle, isn't it? That's how gravitation works. So if the particle is here, all this mass of the Earth is of no interest to us. Let's say that the mass of the Earth total is capital M. Then how much mass is confined in this volume? Density of Earth would be this much, and density multiplied by this volume would be the mass of our interest. That volume is 4 by 3 pi times x cube. So we have m x cube over r cube. This is the mass which is there in this region, and that is the mass which will attract the particle. Outer mass, no use, right? Now, this mass can be considered to be concentrated at the center. So how much force will this mass apply on this particle? Let's say this is m dash. And the answer is G m dash small m divided by x square. Just put the value for m dash and simplify. Capital M x cube by r cube. So we have G m m x over r cube. What would be the direction of this force? Direction will be towards the center of the Earth. Center is the mean position. So if particle is x distance away from the center, force is towards the center. That means the two are in opposite direction. Vector f and vector x are in opposite direction, so that minus sign will come if you like to write in vector notation. This proves that this will indeed be SHM, F equal to kx form. You know what is k now? Can you find out the expression for the time period? And see, if you get this answer, 2 pi under root r cube by gn. And if you have any questions regarding this discussion, then let me know. There's a private message about the location of the tunnel in this figure. I have taken it as vertical. Let me try to put it on the board. Something like this. Something like this. (1600 km) is very significant. 1600 km, just imagine. 1/4 of the radius of the earth. Anyway, we have to assume that again, what we discussed in gravitation topic, that will be useful here. We got two results, one for variation in g with height and one with variation in g with depth. Now one result was approximate result. It was valid for small h, and the other result was in simplified form. One was approximate in simplified form, and the other one was anyway accurate. So in case of depth, what was it? 1600 is by no means small in comparison, that small in comparison to 6400. G dash equal to G 1 minus h by r. Is it the accurate one? Or the approximate one? This is the accurate one. Maybe I can take D for depth. Well, in that case, it is as simple as putting the values 1600 for D, 6400 for R, and then using the formula for time period, which is T equal to 2 pi under root of L over G dash. So please plug in the values and calculate. If you have any questions, then let me know. The answer that I have is 1.47 seconds. I don't see any questions, so I'm moving on. In the last class, I talked about what happens if you keep the pendulum inside the elevator or in a car which is accelerating. Elevator which is accelerating, car which is accelerating. Now, in case of car, if the car is accelerating towards the right side, then pendulum would not be vertical in its mean position, right? Pendulum would be inclined in its mean position. Now, this car can go in circular path also. Imagine a situation like this. This is circle and the car is going like that. Pendulum is there at the ceiling of the car. Imagine the speed is fixed. The speed of the car is fixed. But still, car is accelerating because it is moving in circle. With respect to an observer inside the car, there would be a centrifugal force like that. Now just imagine a pendulum like that and centrifugal force acting towards the right side. Gravitational force is downwards. So we have a similar situation, just like in this case. Centrifugal force, gravitational force. Here, centrifugal force, actually here I should call it pseudo force. Pseudo force is a better term, whether it is circular motion or not. Centrifugal word is more appropriate for circular motion. Both are pseudo forces, this or that. So, centrifugal, gravitational. So the mean position would not be vertical, mean position would be inclined. About this inclined mean position, it will oscillate to and fro, like that. But it won't be, this mean position won't be that. Mathematically speaking, T would be 2 pi root L over G effective, where G is under root of G square, G effective is under root of G square plus A square. What is A here? In this case, if speed is V, yes. If speed is V, then A is V square by R. So in case of this situation, A could be given to you. But in case of this situation, normally speed would be given to you, the radius would be given to you. A is something that you will have to find out. This is nothing but centripetal acceleration. So both cases are handled by pseudo force concept, that case or this case, and they have similar results. Some problems based on angular SHM are tough problems, and I will have to take such problems now. There is some small block performing to and fro motion, but the oscillations are small. Radius is R. This is a concave surface. It is smooth, no friction. Oscillations are small. Then what is the time period? So first of all, we would need to check if this is SHM or not. Obviously, angular SHM or not. If we know it is angular SHM, then it is very easy to find time period. So let us draw a vertical. Let's say this is the center. It could be going to and fro, and at any instant, let us say it is at angle theta. This is instantaneous location. It could be crossing it, coming back towards it, and so on. Now this is no pendulum. That's just a line, no threads. Energy approach is a very useful approach in solving even these types of problems. Energy approach. It is smooth surface, so mechanical energy would be conserved. So we can apply conservation of mechanical energy principle. Height is changing, so gravitational potential energy we will have to consider, and kinetic energy we will have to consider. For gravitational potential energy, we need a reference line. Let's say this is the reference line. I will drag it below. for gravitational potential energy. So total mechanical energy is constant. Kinetic energy is half mv square. V is the instantaneous speed at this point. Then potential energy. Can you tell me, if this is the baseline, if this is theta, then what would be the gravitational potential energy at this point? M is the mass. Basically, you have to tell h. That will be multiplied by mg. mgh. What is this fellow h? R minus r cos theta. If anybody has difficulty in understanding this part, raise your hand and I will try to explain. Okay. Draw a perpendicular from here. Here it goes. From this point to that point it is r. Top to this point it is r. This is also r, radius. So in this triangle, if this is r, this is theta. So from here to here, that will be r cos theta. So this tiny fellow would be total r minus r cos theta. Then that's it. This is constant. When we use energy approach, we differentiate. You will see how it works so well in SHM. Differentiate with respect to what? With respect to time. M by 2 is constant. Derivative of v square is 2v dv by dt. R I can take out. M is constant, G is constant, R is constant. 1 minus cos theta. Derivative of 1 is 0. Then derivative of minus cos theta plus sin theta into d theta by dt. I have applied chain rule. Derivative of constant is 0. So we have mv. What is dv by dt? Acceleration. Which acceleration? Tangential acceleration or radial acceleration? This is circular motion. That's good. Then mg r sin theta. What is d theta by dt? D theta by dt, not d omega by dt. Angular speed. Yes, but you know that omega problem in this topic. So we have been using big omega for angular speed in this topic, right? That big omega. Now, this is circular motion. So V is equal to R omega. Again, this omega. M I can cancel right away. Now we want angular SHM. So AT also we don't want. How do we convert AT to alpha? AT is equal to R alpha. That's perfect. I can remove R. I can remove omega also. What is the condition for angular SHM? Alpha should be minus omega square theta. This omega is of angular frequency. Clearly, this is not SHM. And that is why in the question, it is mentioned small oscillations. If oscillations are not small, it won't be SHM. In many questions you will see small oscillations, but note that in this question of Earth, there was no mention of small oscillations. So whether they were small or big, they would be SHM in this problem, but not in this. So if theta is small, sin theta is theta. And you know the meaning of negative sign. Done. Omega square is G by R, and therefore time period is 2 pi by omega, which is 2 pi under root of R by G. This energy technique is very important. If you have any questions regarding this question, let me know, or I will try to take a harder problem than this one. It rolls without slipping. Now rolling without slipping is difficult unless you have a rough surface. That is understandable. But you know that in rolling, mechanical energy is not gone, not lost. Pure rolling I am talking about. Doesn't matter if there is friction. So that approach will work here. But things are now more complicated because just like Earth has two motions, this ball has two motions. One is like orbiting around the sun type of thing. Imagine this to be sun. So that type of motion, orbiting around the sun, not full circle of course. Second is spinning about its own axis. So as rolling happens, it will spin. So that's how it will work. Stop, turn, stop, turn, stop, turn. That's how it should happen. But we will have to see if it is angular SHM or not. Once we have proved it, finding time period should be no problem. So as it moves to and fro at any instant, let's say this angle is theta, its speed is v, linear, angular speed says omega, angular acceleration alpha, mechanical energy is conserved, height is changing, so I need some gravitational potential energy reference which I am taking as this. Kinetic plus potential. Kinetic. It is pure rolling. Kinetic energy in pure rolling is given by half m v square plus half I center of mass omega, but this omega is this omega. That is kinetic energy. Then comes potential energy. Can you tell me how much is potential energy? That lowest one is right. Potential energy you have to see from center of mass. Place a particle here. So from here to here, the distance is r minus r. Now do the usual thing, drop a perpendicular. No, just a moment. I think that answer would be correct if I take baseline not here but here. So where its center was in the very beginning, we are taking our baseline passing through that center. So initial potential energy is 0. I mean here at mean position it is 0. From this point to the center, distance is r minus r. From this point to the center, it is r minus r. So from here to here, it will be r minus r cos theta. So now this answer is correct. R minus r, 1 minus cos theta. If you have any questions, let me know. Fine. So this is constant. Now the usual thing, differentiation with respect to time. M by 2 is constant, twice v dv by dt. ICM is constant. Then d omega by dt. Mg constant, r minus r constant, derivative of 1, 0, derivative of minus cos sine, d theta by dt equal to 0. dv by dt is tangential acceleration. Then I, center of mass, omega, d omega by dt is alpha. D theta by dt, that is omega, this omega. We are interested in angular motion, so let's get rid of v, let's get rid of at. V is actually vcn, center of mass. Maybe I can write it everywhere. Center of mass is a particle. And while other particles inside the ball are performing very complicated motion, center of mass is not performing complicated motion. Can you tell me which type of motion center of mass is performing? What does that mean, angular motion? We have not yet proved that it is angular SHM. We have not yet proved it. You can say it is moving in circular paths. Are others moving in circular paths? Not strictly speaking. when there are two motions superimposed, just like Earth, will somebody sitting at heliocentric frame somewhere in space, will that person say Earth is performing purely circular motion? It is revolving around Sun, but also revolving around its own axis. But center of mass of the Earth, that one can say from such a frame, is almost circular. So center of mass is performing circular motion here. So for VCM, I can write VCM is equal to how much? VCM equal to, for circular motion, R omega. In that you cannot write for any particle inside the sphere. For any other particle inside the sphere, you cannot write this. I hope you are understanding this point. Only for that point called center of mass, you can write this. VCM equal to R omega. But which R? R minus R, right? Omega. Then A tangential is R alpha. Now technically I can add one more thing. This A tangential has been obtained when we differentiated dVCM by dt. dVCM by dt. So this A tangential is for center of mass. There are otherwise so many particles inside the ball. It is ACM tangential. It makes it a little big, writing it. It is ACM tangential. Maybe I can write T up. So because it is for CM, which is performing circular motion, this formula is for circular motion. A tangential equal to R alpha is for circular motion, and center of mass is performing circular motion. What is ICM for spherical ball? That you must be knowing very well. Two by 5 mr square. Let's cancel m. Let's cancel omega. We are interested in alpha. This is not looking very good, but the question says that large radius capital R that should allow us to make some approximation. If I had been, as I can see that private message, if I had been 2 by 5 m r minus r square, things would have been very convenient for us. But I is ICM, right? About center of mass. So because it is about center of mass, shouldn't it be just r square, small r? So we will have to make some approximations. Let's proceed further and see what happens later on. Let me copy this bottom thing to the next board. Now this thing is constant, but even then it is not SHM because of sine theta. But the question says small oscillation. Small oscillation. So taking sine theta as theta, putting approximate sign in place of equal to sign. Now you can see we are done. Omega square is this. And therefore T is 2 pi by omega. We will make approximation later on. Now before we do that last stage of approximation, in case you have any clarification about radius, should it be r minus r or r, whatever, then let me know. It can act as a final check also. In any step, if you think the radius should have been different, then let me know. If there are no questions, then let's see what we can do in the final step. So there is one point. Yes, there is one point that has been missed. There are two circular motions here. The problem is that there were two circular motions and they were taken as one. One circular motion is this, which center of mass is performing. Second circular motion is this, due to rolling. The big omega we have been using for SHM, angular SHM. So big omega is for this d theta by dt. But when we write half ICM omega square, then that omega is not due to this circular motion, but that omega is due to this circular motion. So that's why I had to make it omega dash. This is not that omega due to which you are having this type of thing. This omega dash is due to this. How do we connect omega and omega dash? This is the way to connect two omegas. VCM is a particle performing circular motion about this center. CM is a particle performing circular motion about this center. So using that condition, VCM will be R minus R omega. VCM is also performing linear motion, and this is a circular motion. For pure rolling, VCM is given by R omega, whatever omega is there, which I have taken as omega dash. That is the way to connect the two omegas. So what will happen is that omega dash, this is omega dash, then this is not going to get cancelled, but omega dash is R minus R by R omega. So when you put that here, well, that's the good news. You will have R minus R by R, and that R square gone. Well, that is simply great. So looks like we won't need approximation of capital R being big. So that's what it could become. And then 7 by 5 it will become. 7 by 5. This will go. Seven by 5, that will go. 7 by 5, that will go. Then this fellow, that fellow gone. So it will become 5 coming to the bottom, this thing. So this was the thing. This particle is performing double motions about this circular motion, and in pure rolling, for pure rolling, different omega should be used. This motion, different omega. And for this center has changed, so different omega should be used for this circle. For SHM, which is about this, SHM is about this, we have used just this omega, and for rolling, we have used this omega. So if you look at this step for kinetic energy is written for rolling motion, right? It is written for rolling motion. And for rolling motion, omega should be omega dash, not SHM's omega, which is about this point. So that was the thing which created trouble. And when we differentiated, we got dVCM by dt, and that is the SHM's omega, just omega, not omega dash. Look at this, just omega. So one was omega, other one was omega dash. And then we connected the two in this board number 8, and that's all the problem. So please make the correction, and if you have any questions, then let me know. We stop now.